Okay, in this video, we're going to talk about closed and open manometers. It's an old-timey thing. You don't see them anymore, but you do see them sometimes on the AP test and maybe even on the IB test. So, closed and open manometers. Here we go. First of all, we've talked about this. This is an old drawing of like what an original barometer might look like. You would have this test tube looking thing, and you would have this part inverted like this. You fill it all the way up to the top with mercury. That's a G. You put your finger on here like this. Don't do that because it causes cancer. Turn it upside down and put it into the pool of mercury. Don't do that because it causes cancer. And let go of it. And when you do, it's going to drop this little bit right here, just this little bit. When it drops, there's no gas going in. So what is above here is strictly a vacuum. That's a lack of mass. There's nothing there. Nothing can't push and nothing can't pull. In fact, the only things that can pull are gravity and magnets. Now, once this happens, what's the reason that this column of mercury is still sticking up is because we have this pressure pushing down on top of the pool of mercury. Air pressure is constant. We're in the bottom of a sea of a gas ocean. The particles are constantly bombarding this top of this mercury. And as those particles hit, it causes a force. And it can compared to the area above it, then what we're talking about is applying a pressure to the pool of mercury. Well, this pressure is a fluid pressure. It pushes in each and every direction, which is down, across, over, but also straight up the tube. So it's also applying a pressure straight up the tube, and that's what's holding the mercury up. If you could solve this off right here and then weigh this, this would be the mass or the weight above a cross section would be an area, and therefore the weight, which is a force over area, would be pressure. But instead of doing all that kind of math, we just measure the height of the mercury. So this is 760 millimeters high, and that is considered to be standard pressure if you're in America. If you're an IB, it's a little bit less than that, and it's really confusing. Now, what happens is if the outside pressure increases a little bit, these forces get a little bit bigger, the force pushing up gets a little bit bigger, then the column of mercury will actually rise a little bit. So now we may be at like 764 millimeters high, and therefore the height of the mercury is a measure of pressure. And of course, if it drops and the outside pressure is less than it was a minute ago, then there'd be less force on top of this pool of mercury and then less force pushing up. And the force pushing up will equalize right here with the force pushing down, meaning the weight of the mercury over weight is a force over the area is going to equal to the pressure outside. So if this thing drops in pressure a little bit, then the column actually drops and maybe down to like 754, who knows what numbers. So that is how an old-timey barometer works. That is why we have a linear measurement of a column of mercury to equal to pressure. And of course, just for review, 1 atm atmosphere equals to 760 torr, which is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals. This is what we used to consider to be standard pressure until IB changed this one into 100. So if you're doing a comparison of pressures, these are the ones you kind of want to learn. If this was actually 100, then these would all be a little bit less. Nobody wants to do those calculations. So here is a closed-in manometer. It's called a closed-in because this guy right here on the top, it's closed. So no gas goes in and out of that area. And the way we calculate this area here, this area here, these are vacuums. So there's nothing pushing down or pulling up on the column of mercury. It's always easier when it's a column of mercury because it matches up with the linear measurement we just talked about. So closed-end manometers, this side to the right is going to be a vacuum, doesn't affect it one bit. Right now, this diagram on the left is showing that there is zero gas here because when these things are equal on manometers, as you can see, the line going across is straight across, and I don't know, straight the way I drew it, and therefore the pressure on one side is equal to the pressure on the other side. This mercury is pushing down. This mercury with an equal height is pushing down with the same force over the same area, and therefore they're equal. So what equals to no pressure from the right side? Be no pressure from the left side. But then what happens is we are going to create some gas. Either you have a confined gas or this will vaporize. The liquid's going to bubble up. It doesn't have to boil like it's shown in the diagram. It's going to bubble up or just evaporate. Fill this side with some kind of vapor. If there's any kind of gas vapor over here, it causes a pressure. The pressure is pushing down on the mercury. And then since this side is pushing down more than this side, because this side isn't actually pushing down at all, then it's going to go up on the right and go down on the left. Now, if we draw a line straight across, that means that everything below that line has no effect because the volume and mass of the mercury here equals to the volume and mass of mercury here. So that's a wash. There's nothing. So what's the difference? Well, on this side, we have gas pressure, pressure of the gas. On this side, we have pressure due to the mercury, not vapor, but literally the weight of the mercury over this area here. And therefore, you have a physical pressure of liquid mercury pushing down. Well, when this thing settles and this is the height, then they're going to be equal. So the height of this mercury on this side is going to equal to the gas pressure on that side. Open manometer. An open manometer has a hole right here, which means the air pressure plays a big part. Air pressure is pushing down. This isn't necessarily 1 atm. This is just the actual atmospheric pressure. Let's say that the atmospheric pressure is 98 kPa. Well, with the line right here being even, just like we said a minute ago, the mercury pushing down on this side and the mercury pushing down on this side all cancels out. Has nothing to do with it whatsoever. So the pressure pushing down on the right side is equal to the gas pressure pushing down the left side because the column of mercuries are equal. And therefore, if you have a barometer outside and say it's 98 kPa, then the gas pressure inside is 98 kPa. That is an open-ended manometer in which the mercury levels are equal. We're going to have two other options. One is it's going to be bigger on the right side or taller on the right side, and the other one is going to be taller on the left side. I'm going through this pretty quickly. You can obviously stop, rewind, and listen to it again. I know my voice is quite amazing. It's a voice for radio for sure. He said sarcastically. Here is an open-ended manometer in which the mercury is higher on the gas side and lower on the atmospheric side. So again, if we look at this line right here, everything below it doesn't matter. So what's on the right side? On the right side of pushing down is going to equal to the left side pushing down. And the right side pushing down is the atmospheric pressure, the pressure of the atmosphere. And that's going to equal to the column of mercury pushing down. So that's going to be the mercury column. And again, we can just measure this by millimeters of mercury. And this gas pushing down as well. So there's two things on the left pushing down. So we'll put down the two things. We'll call this gas pressure, something really original. So the gas pressure pushing down combined with the mercury pushing down on the left equals to the outside pressure pushing down. So guess what? This is algebra. I need to know 2 of the 3. They would probably give you the atmospheric pressure. Let's say it's nope, I don't want to do 98. I want to do millimeters of mercury. So let's say it's going to be 745 millimeters of mercury. For that guy, we can see the height here, right? We can see the height difference between this guy and this guy. Now they may give you this height. They may give you this height. They may give you this height just to confuse you, but you need this height. And if this height is, let's say, 80 millimeters, then we can say that this guy is 80 millimeters. And I would call this guy, I have no idea, and therefore it's X. So we subtract 80 from both sides. You end up with 665 millimeters of mercury, and that's what the gas pressure was. So they need to give you all but one. That is one open-ended manometer in which the left side has less gas pressure than the right side. So almost exactly the same. Let's pretend like the atmospheric pressure, they say it's 1 atm, so that's 760 millimeters of mercury. If they said that this was, let's say, 140 millimeters, and that this was 50 millimeters, that means this must be 90 millimeters, and it's mercury. So really the one we want to know, whether we do subtraction and math, we want to know the difference in the columns. Again, this is a wash. This side and this side are the same, and therefore they're equal, and therefore they have no effect. So now here's the difference. We said it was 90 millimeters of mercury. Now, at this base right here, the left side and the right side equal. What's on the left side? The left side is strictly gas, only gas. So pressure of the gas equals to the right side. What's on the right side? Well, the right side is atmospheric pressure. So we said the atmospheric pressure is 760. Oops, 760. The gas pressure, we have no idea. And then we also have this column of mercury. So the column of mercury here is also added too. So the air pressure is pushing down and the mercury pushing down. That's two forces pushing down over the same area. And therefore we have the pressure of the mercury, which we said was 90. Nope, 90. We're just making up numbers. So now X is going to be the 760 plus the 90, or it's going to be 850 millimeters of mercury. We can convert that into kilopascals if we wanted to. That is your tutorial, very fast tutorial on open and closed-end manometers.